Okay, so this lesson we're going to take a look at how the message is actually passed along the neuron. There are some great animations and videos, and I'll show you probably a couple of those, or show you which ones you should definitely focus on. But we're going to do it through a very basic set of drawings. So we'll get you to do some drawing so you can have them to kind of remember back to, and then hopefully it'll make more sense when you do watch the animations and videos. So the kind of messages that travel within the nervous system are referred to as electrochemical messages. And we've mentioned that before, but now we're going to look at what they mean by it. So I'm just going to get a little pen here. Try. Okay, so the electro part is a wave or region, so a wave, right very well. Okay, a wave of depolarization. So when we say something is polarized, we mean that there's a distribution of charge. Okay, so there's a positive area and a negative area. Okay, so when we say it's a region of depolarization, it means that the charges have switched. Okay, there's charge reversal, in other words. So if you're reading about this part of the message, they might call it a region of depolarization, a wave of depolarization, or they might call it the action potential. Okay. In any case, this region moves from the dendrites along the axon towards the axon terminal. So it's always in that direction. Okay. The chemical part of the message is really the transmitting of neurotransmitters between neurons. Okay, so you're going to learn that the electric message can't jump between neurons. So there has to be a way of getting the message from one neuron to the other. So the chemical part of the message accomplishes that. So there's neurotransmitters that are stored in what we call the presynaptic neuron, or the one that is in front of that little space or gap. They travel along or travel across that gap. So the gap is the synapse, travel along the synapse, and they bind to the dendrites of the next neuron. So because it's after the synapse, we call it the postsynaptic neuron. And they will either stimulate that neuron and help to bring about a new action potential or a new electric message, starting the message in the next neuron, or they may inhibit it from happening. Okay, so that's an overview. So the first part, we're going to take a look at what it looks like along the axon. We'll take a piece of the axon. So I don't know if you can see this little neuron down here. So if we were to take a little piece of it, say that piece, and we blow it up, okay, we're going to do a little bit of drawing to show you what happens. We're going to do a little drawing to show you what is happening in the resting neuron. Okay, so actually I should show you, in case you don't have it and you want to draw along with us, if you go to our class site, go to our class site and go to the class notes page. Okay, what I'm using right now is this action potential handout. Okay, so the action potential handout will allow you places to jot down information about how the electric part of the message focus on the electric part of the message and how it is transmitted along the neuron. And then, in the next video, we'll probably be covering what happens across the synapse, so the chemical part of the message. So it would help if you had that in front of you so you could sketch along with us. Okay, so if you were to read through all this, and we will cover it, not so much as reading as sketch it and then we take a little section of the axon and we're going to blow it up. Okay, so for those of you who had Bio 521, then you'll probably recognize these things as being part of the cell membrane. Okay, so these are phospholipids, and they have a polar phosphate head, so the little circle is polar and it likes water. Okay, but the little tails, they're fatty acid tails, and they're hydrophobic. They don't like water at all. Okay, so I'm going to draw the cell membrane. Okay, so the cell membrane is made up of a bilayer of these phospholipids, okay, so fatty stuff, and within it there's a lot of different proteins and other things embedded. Okay, so there are certain ones. If I were to what? Quicker if I just let go. Okay. Quicker if I copy and paste these. Alright. There we go. Okay. So I'm going to do the bottom part. So along the bottom of the neuron, so we have membrane all around, right? So this is the bottom part. I'm not going to really show any of the things that are embedded. Okay, so we'll just say this is the bottom. And we have a little bit of space. Okay, and then so this part here is the top part of the neuron. So the space in between would be, let's see, I can do text. The space in between would be cytoplasm, or you could say intracellular fluid in here. Okay, and oops. Out here would be extracellular fluid or extracellular space. It's fine. And I'm going to, sorry for all the clicking. Okay, so it's extracellular outside here and also extracellular above here. Okay, so we're talking above the neuron and below the neuron. Above the axon and below the axon, those are both extracellular or outside of the cell spaces. And they have fluid in them. That's watery, so we call them extracellular fluid. And that's why these polar heads will orient themselves towards the watery fluids, and the fatty acid tails turn inward and make a phospholipid bilayer. Okay, that's typical of any cell membrane. Now, what they do have, I should really move this down a little bit. What they do have embedded in the cell membrane are certain proteins, again, that have certain jobs. And in a neuron, there's a lot of ion channels, certain ion channels. So we're going to do a little sketch here. Won't be as difficult after the first few. Okay, so when the neuron is resting, there's one ion channel that is kind of leaky. Okay, so it's open a little bit. Okay, just as simple as there we go. Okay, and then there's another one. We'll do it a different color. That is closed. So that one, the door is closed. I know you guys are going to take a little longer to draw these. And we also have another kind of protein that's actually a pump. Why is this being so finicky? The pump has, it's hard to draw. Okay, let's try again. Kind of three spaces, one kind of ion, and then it has two spaces. These are kind of symbolic drawings. There. Two spaces for another kind of ion. Okay. There. Okay. So, if you read through here, it talks about the fact that in the resting membrane, some different color for the text. In the resting membrane, the one that's leaky, if you read, the one that's leaky is the potassium ion channel. Okay, and the one that's closed is the sodium ion channel. And the one that has spots for two different kinds of ions, that is the sodium potassium pump. Alright, so, oops, I apologize for being so finicky. So here is the sodium channel. This is the potassium channel. and this one is the sodium potassium pump. Okay. But I'm doing a video lesson. Okay, sorry. Okay, so basically, oops, I wish I could do without a mouse. Because this channel is leaky, potassium ions can go to the outside. Okay, sodium ions, because that channel is closed, they are stuck on the outside of the membrane. Okay, so we end up with high levels of sodium on the outside. That's an A. Because these potassium ions help to drive the sodium potassium pump. As a pump, it's going to take ATP too. Okay, it's going to take energy to make it work. But what happens is this pump pumps for every two for every 2 potassium ions it pumps in. Okay, so shouldn't make those cross, but anyway, for every 2 potassium ions it pumps in, it pumps 3 sodiums out. That's supposed to be Na plus, Na plus. Okay, so for every 2 potassiums it pumps in, it pumps 3 potassiums out. And if that sodium channel is closed, then there's a high amount of sodium on the outside and usually a pretty high concentration of potassium. Okay, even though it can leak across, it keeps getting pumped back in. So a higher level of potassium would be on the inside. Now, there are other ions floating around too. So what they find is the net charge. Okay, so the net charge of the membrane when it's resting is positive on the outside and negative on the inside because there's so much more sodium on the outside with reference to the amount of sodium or potassium on the inside. It's much more positive on the outside of the membrane. Okay, so it makes there be what we call a resting potential across the membrane. Okay, so the charge different is negative 70 millivolts. So negative 70 millivolts. So that is when the neuron is at rest and not firing. Now, it doesn't mean that there's only one of each channel and one pump. It means this is just showing you a little section to give you an idea of what they look like. So there's lots of channels and pumps across the neuron, across the membrane. And they'd be on both sides. Okay, we're just doing a simplistic drawing of it. Okay, so that was more complicated. We drew the membrane on both sides, okay, in more detail. We drew the receptors that are the channels that are opening and closing. Now we're going to take a look, but we're going to simplify the drawings. Okay, oh, shoot. Okay, so let's say this is the membrane that we just drew the channels in, and this is the membrane on the other side. Okay, so this space in between, again, would be cytoplasm, and on either side, up or above or below, would be extracellular space. So we just said that in the resting, membrane of the neuron, big screen, okay, in the resting membrane of the neuron, we have lots of sodium on the outside and lots of potassium. Okay, lots of potassium on the inside. What's this in here? There. Okay, we also said that the net charge, oops, color, it is positive on the outside and negative on the inside. Okay, so when there is sufficient stimulation, we have okay, when there's sufficient stimulation, the sodium channels that were closed will start to open. Okay, so the sodium starts to leak in. So we can show this on here like this. Okay, so the sodium starts to leak in. And once it's leaked in a certain amount and has made the inside of the membrane more positive, so once it gets to from -70 to -50, so it's gone up, then the channels all kind of open really wide and let the sodium rush in. Okay, so it changes the charge. Okay, so if you want to, you can add a little bit of text here. Text here. Still not working. Okay, open. Let's say sodium channels. Oh my goodness, this is difficult. I wish it was a touch screen. Just seems so rough. Okay, sodium channels open. We'll get it down to a science for the next one. Okay, sodium channels open, so that means the sodium is going to come in. And we call this process where the sodium channels are opening and the sodium starts to rush in, we call it depolarization. Okay, where the charges are reversing. So all right. Oh, there. Okay, so sodium channels have opened. Sodium starts to rush in a little bit, and then all of a sudden gets to the point where they open wide, and a big rush comes in, and it makes it so we have lots of sodium on the inside. Okay, we also have, lots of potassium still on the inside. Okay, so if we moved all those extra positives to the inside, then the net charge ends up being positive on the inside, negative on the outside. Okay, and we say when that happens, we say that it is depolarized. Okay, the charges have reversed. Instead of being positive on the outside, it's now positive on the inside. Okay, now we're going to do the same kind of thing, but for the next stage. What happens next? All right. It's going to be a similar kind of setup. I'm going to take this one, and I'm going to put them over here. Okay, so this is where we just finished off. Okay, lots of sodium now on the inside, lots of potassium on the inside. So now the inside of the membrane, inside the cell, is more positive. The outside is more negative. Okay, so it's depolarized, we said. Now, we've seen that in order for the neuron to fire, as we say, in order for it to have the message, it has to be positive on the outside, negative on the inside. And we need the sodium ions on the outside. Okay? So what can happen? Well, we had just opened the sodium channels, so that's not going to help. The sodium's not going to go back out because it just came back in. But let's see, we could open potassium channels. Okay, we open the potassium channel, then what way is the potassium going to go? Well, it's high on the inside, so it's got to go out. Potassium leaves the neuron, goes outside. Okay, this process we call repolarization. Okay, so we're trying to get it back to the normal charges. If we do that, then end up with high potassium on the outside and high sodium on the inside. Okay? So charge-wise, this becomes positive again. Not quite as positive as normal. Not as much of a difference as when we started the process in the resting neuron. Okay, but it does become more positive on the outside than on the inside. Okay, so then we say, when that has happened, it's considered repolarized. Okay, but it doesn't stay that way for very long. The last phase, which kind of almost happens right with the repolarization. It happens almost like it very quickly. Okay, the last phase is we need to get the sodium on the outside and the potassium on the inside. Okay, so we've worked with the sodium channels, we've worked with the potassium channel. Okay, oops, I'm gonna do that same thing. You've got to do something in order to get the ions back on the proper side. So, I should have these ready to go, but I wasn't quite sure how it's going to work out. Okay. The good thing about watching a video lesson is you can pause it at any time so that you can take the time to draw. So we're going to put here where we had left off. Okay, so first the sodium channels had opened and the sodium rushed in and the charges were opposite. So we said it was depolarized. And the last one we drew about, okay, the sodium channels were already open, so couldn't really do anything then. The sodium had already rushed in. So we opened the potassium channels. Potassium floods out. So now we consider it repolarized because there's lots of potassium on the outside and lots of sodium on the inside. The charge is back to normal in that it's more positive on the outside, not quite as much as normal, but at least the net charge is back to the way it was, more positive on the inside, I mean. So the last part is we need to get the ions on the right side. Okay, because in order for the next action potential to happen in that area, in order for it to get started, you need to have the sodiums on the outside and the potassiums on the inside. Okay, so to make it happen, you got it. We use sodium, potassium, pump, kicks in. That's really proper. Okay, does its job. That's not even right either. Not very good terms, but it's just to give you an idea. You're not going to have to draw all these for me, but it is to help you understand, okay, what it is that's happening, what's flowing which way. So, remember, we look back here, okay, sodium, potassium pump. Pumps 3 sodium out for every 2 potassium in. Okay, so we go back to here. Oops, there we go, there. I'll take the pen. Okay, so for every 2 potassium in, for every 2 that go in, doesn't mean it's just taking 2 in, just the number it can take at a time. Okay, it sends 3 sodiums out. So we end up with lots of sodium outside and lots of potassium on the inside. And we get the charges back to, oops, charges back to the proper levels. Okay, still positive on the outside because we'd already dealt with repolarizing it. Okay, but now it's to the proper level. So we say this period is known as the refractory period. And we get it back to its resting state. So it's ready for another neuron, or ready for another action potential to pass along it. So let's take a look and see what this looks like. Oops. Oh, that link doesn't work right. I'll go here. Okay. We'll take a look and see what this looks like. So here's the potassium channel and the sodium channel in the resting membrane. Okay, there's a sodium-potassium pump working. So there's lots of the green ones, which are sodium, on the outside. Okay, lots of sodium on the outside and some potassium on the inside. So, in order for the action potential to happen, if you remember, the sodium channel is going to open. This is a little test, and they want you to basically change the gates. Which one should be open, which one should be closed when the action potential happens. So when the action potential happens, remember in a resting membrane, the sodium channel was closed and the potassium channel was open so that they could make the pump work and make sure that lots of sodium stays on the outside. Okay, so when we have the action potential happening, potassium channel closes and the sodium channel opens. Opens a little bit at first, and then once a little bit comes in, once a little bit of sodium comes in, it causes it to open up wide and changes the net charge on the inside. So the graph up here is showing what happens to the charge. So charge is negative 70 millivolts. Okay, so the negative is inside the membrane. And once the sodium starts to come in, that charge is going to start to go up. And then it's going to go up really fast so that it's positive on the inside and negative on the outside. So let's see what happens. See if we're right. Oh, submit, it says. Yay, we're right. Okay, so when the potassium channel is closed, sodium rushes in. And if you look up here, okay, see it causes the interior to become more positive. This is what we refer to as depolarization. Okay? So, the next phase is repolarizing it. We need to get the charge back to normal. So since the sodium channel had already been opened, and there's lots of sodium and potassium on the inside, now, oops, we're going to close it and open the potassium channel. Okay? So if we open the potassium channel, remember, there's lots of both sodium and potassium on the inside now. If we open the potassium channel, you're right, the potassium is going to flood out. Let's see what happens. Potassium is purple. Okay, so the potassium goes out. So now, if you look, the charge has reversed itself, so it's gone negative on the inside again and positive on the outside, but now we have to get it back to normal. Okay, so the last step is the refractory period, where the pump gets things back to normal, brings all the sodium to the outside, and that's powered by the potassium moving to the inside. So we're ready for another action potential to happen. Okay? sorry. It's asking us to click on the thing that's responsible for getting the ions back in the right position, and I wasn't paying attention. So we click on the sodium-potassium pump, and this is kind of a cool fact. It says an animal at rest uses a third of its energy in order to power this pump. That is a lot of energy. Okay, but if you imagine how many neurons you have working at any time, it makes sense. Okay, so if we take that neuron, okay, here's the action potential. It's a wave of depolarization. Okay, so you can see where it's happening because it's a wave where the charges reverse. And it propagates itself, or it keeps itself going along the axon until it gets to the axon terminal. Okay, I'm going to show this again. So we know that the message always moves from the dendrite end to the axon terminal end. As it's moving along, when the sodium comes in one area, it kind of triggers the action potential to start on the next area ahead of it. Okay, so if I'll let it go a little further. I'll let it go a little further. Okay, so we know from looking at this picture that the action potential is moving to the left towards the axon terminal. So that means that right where that blue flashy part is, that is the actual action potential, where the message is at that given time. It's the region of depolarization, or wave that happens. Okay, but this is where it is in right now. So ahead of it is resting. Right in front of it is resting, waiting for the next message to come along. But behind it is where it's repolarized. Okay, a lot behind it would be resting again, but right behind it, it's repolarized. So the charge has been reversed again. It's gotten back to normal, but the ions aren't on the right sides of the membrane. If you remember, we end up with the potassium on the outside and the sodium on the inside. So the message can't go backwards because it still has to get back to normal, where the sodium is on the outside, like up here in front of the message. The sodium is on the outside, potassium is on the inside. Okay, so that is how it passes along. So we can watch it reach the axon terminal. So that's the electric part of the message. I hope that helps to make sense. Okay, so in the next video, we'll talk about the chemical part of the message. If you want, you can read ahead, you can watch the animations and feel a little more prepared. We will be covering it in class, okay, but here are some terms we didn't cover in class on Friday, but we will be, okay. First of all, you need to know about the gap, okay, the space. So this is the axon terminal, so where the message just ended at, okay, the end of the first neuron, and then there's a space between it and the dendrites of the next neuron. So this would be the dendrite of the second neuron, and this would be axon terminal of the first neuron. Okay, and the space in between we call the synapse, or the synaptic cleft, some will call it, okay, or the synaptic gap. Those are all different terms that you may hear describing the same thing, but it's basically the little space that is between neurons. And you can have, this is the dendrite of one neuron, and it can be married up to the axon terminals of many neurons. Okay, so it's through kind of a combined stimulation that we end up either inhibiting or stimulating a message in the next neuron. Now, in terms of vocabulary, because this neuron is the one that the message travels on before the gap, okay, the message would be going, let's see, pen, the message would be going in this direction, right? Okay, so since this is the first neuron, we usually call it, you can see it underlined here, okay, it would be the presynaptic neuron. Whereas the one after the gap is the postsynaptic neuron. So those are important terms that you should know and understand. Okay. Normally, in order to cover the chemical part of the message, I usually assign these questions. Okay, and then the first is to actually label the neuron and the gap, and both the pre and postsynaptic neurons and the regions along the neuron and things like that. And then I get you to answer certain questions about it. So tell me, what are the steps that happen whenever the electric part of the message reaches the axon terminal? And then it asks about some of the different neurotransmitters. So if you have some time, you can pick away at those, or if you are going to be going away, you can pick away at those, and they will also be covered in the next video lesson. Okay, but to do them, you would need the chemical synapse handout. So that one is the synapse handout. Okay, so it's just a blank one that you get to label and then describe what happens. Okay, please, anytime if you have questions, don't be scared to ask. That's what I'm here for. Oops, wrong one.